Good evening. Thank you all for coming, and it's a pleasure to be here. As I actually was an undergraduate at Harvard, and think of this theater as the place that you get to see all the great old movies. So it's really kind of fun to be on this side of the stage as well. In fact, I felt entitled because I do actually quote Casablanca in my book because when I'm talking about creativity, because I talk about creativity being in part about asking small questions and big questions at the same time. And I refer to these three people don't amount to more than a hill of beans. And I think, well, they're the reason I'm watching the movie. So I think these small details are what we focus on when we're doing science, but it illuminates some of the big questions that we have out there. I'm also aware, as being here, though, that I'm going to give a talk. It will have some technical aspects to it and some less technical aspects to it. In fact, when I gave this talk in London, the person who introduced me at the end said, well, the book is really understandable. In fact, somewhat more than the talk. So, but there's a lot of exciting ideas. So I just want to give an overview, both of the physics and sort of some of the underlying ideas. And there's only so much you can do in an hour, and I do more than we should. So, but there will be questions at the end, so feel free to ask. Okay. So I'm going to start with a quote from singer-songwriter Suzanne Vega, which I think is really nice because it expresses both what we're doing in science and also what we do in particle physics, which is my field of expertise, theoretical particle physics. And the quote is, "And what's so small to you is so large to me. If it's the last thing I do, I'll make you see." And I like it because it both expresses the idea of what I just said. In science, we're often focusing on small questions, but with the hopes or with the understanding that a lot of the times it's these small, approachable questions that can illuminate big ideas, underlying big ideas. We all know what the big questions are at some level, but the question is how you make progress. And it's often those small cracks that are ignorable by some people that will sometimes shed light and give us really new insights. But of course, I'm also going to be talking about the world of elementary particle physics, what underlies matter that scales much smaller, far, far smaller than anything you can see with the naked eye. And of course, I also think that it's a big deal what's there. So the quote I'll also take to refer to that. The next slide is also kind of unusual beginning. You might say, why is it doing that? What's it doing there? And you'll find out in a minute. So it's a slide someone sent me. You might recognize the city from the Eiffel Tower in the background and the kiosk with an affiche on it, the big boulevard, so you can tell it's Paris. What do I want you to notice here? Well, what I want you to notice is how much our vision is a function of the scale at which with which we look at things. Of course, if we had very big, very close resolution, very accurate resolution, we would see something that looks very different from that picture of the Eiffel Tower. We would see the iron grid work. And of course, if we looked even closer, we would see the atomic structure that underlies that. So we would see something very different if we looked with very high resolution at a very small scale than the scale with which we just viewed that Eiffel Tower from afar. But of course, what's really relevant for when we're doing science as well is that if our resolution was too poor, in some sense if the scale is too big, we wouldn't even really know the Eiffel Tower was there in the first place. And it's such an obvious fact about the way we view the world, but it's also critical to what we're doing when we're doing science. How we look at things, what resolution we have, is critical to telling us what we will be able to see and what it is we're going to find out. And so the theme of scale, as we'll see, is important in sort of understanding the role of the kind of physics I do, which is extreme distances, both the extreme small distances and extremely large distances. But the real reason that I wanted to show that picture was because if you blow up the poster, you see my name. So what I will eventually get to in this talk is how my name ended up on an affiche near the Eiffel Tower in Paris. Okay. But I'm going to start by talking about scale. And if we just sit back for a minute and we think about what we see, I mean, a lot of the time, one of the reasons I wrote this book, I'd written one other book before, Warp Passages, which was about extra dimensions of space and particle physics. And even people who are extremely interested in the topic, I think, are often confused about the reality of it and how it compares or how it fits into the world we have in our daily lives. So I think this scale is a very important concept by which to understand what's going on. And in particular, it's very important to recognize that our intuition is shaped by our vision, by what we see in our daily lives. And if you think about it, our vision is fairly limited. We see basically with the naked eye, scales ranging from maybe millimeter to kilometer. And in fact, optical wavelengths are a few hundred nanometers. That means that if you had something smaller than that scale, there's no way you can resolve it with visible light. It would be as if I took a blanket and put it over this room and asked where any one of you was sitting. You need the resolution on a scale of a seat to be able to find any particular person. And in the same way, you need a wavelength that's small enough that it can identify some small object in order to be able to isolate anything on a small scale. So that tells us right away that if we're going to understand the universe on very small scales, we're going to have to do something that seems fairly unintuitive to us at first. We're going to have to use technology to get to scales beyond the scales that we see in our daily lives. So before continuing the rest of the talk, I thought it would be a good idea to just take a very brief tour of these scales, both the large scales and the small scales, to get an idea of where everything fits together in terms of the sizes that are involved. So we'll first start with large scales, talking about large scales. And keep in mind that a human scale, the scale we're familiar with, is about a meter. Each of us is roughly 2 meters tall. There might be variation by as much as 15%, which seems huge, but basically we're all about the same size. We're all a meter to 2 or 3 meters tall. But the universe, of course, spans a much, much broader range of scales. And in fact, the known universe is 10 to the 27th meters across. That's 1 with 27 zeros. That's a huge, huge number. And why do I say the known universe? Well, that's because the speed of light is finite, and the universe that we know has existed a finite amount of time, which means that the known visible universe has a finite size. Of course, that doesn't mean that the universe as a whole can't be infinite or much bigger. It just means that we will not make observations beyond that scale. That is the scale of what we can make observations about. And it's an enormous scale, much, much bigger than human scale, of course. Now, within that universe, of course, there are many different size scales. There's a huge span, galaxies of 10 to the 20th meters, solar system 10 to the 13th meters, the Earth itself 10 to the 7th meters. But one thing to notice about this is that even though we're spanning 27 orders of magnitude, the laws of physics that apply are the same. We'll use the same laws of gravity, the same laws of electromagnetism to put together what's out there and how it functions. That should be contrasted with small scales. So now let's go away from the larger scales, bigger than human size, to smaller scales, smaller than human size. So we now have the human at the top, a couple of meters tall. And now we're going to go inside and see what underlies this human scale. And one thing that's interesting is, although we think of physics as very foreign sometimes, but even with biology, until we actually had the tools to open living beings up and look inside, people didn't know what was there. Once they could, of course, they could then, once you could look under a microscope, you could see red blood cells. Once you could cut people open, you can see the circulatory system. No one knew about the circulatory system until you can cut animals or people open and see veins and arteries and try to figure out how it all worked. And of course, cells you needed a microscope. To see DNA, you needed X-ray diffraction. So you needed tools to be able to get inside, to be able to see what's there. And that is generally the story in the advancement of science. We have scales that we can see that we're familiar with, that we've seen before, but to go beyond that, we often need to develop new tools that allow us to see what lies beyond. And of course, in the world of physics, that happened in a revolutionary way when people were able to look at the scale of an atom. Once they could look at the scale of an atom, they could see that the laws of physics themselves, the way we formulated physics, changed dramatically. We went from classical to a quantum mechanical description, which is really quite different in its very formulation. Even the kinds of questions that you ask are different. And then once you go inside that atom, you see, even though some people, I personally find it amazing that atoms were really not known until the turn, not of the last century, but the previous century. So they're pretty recently known. Of course, people say, well, the Greeks postulated atoms, and they did, but they postulated unchanging, indivisible objects, whereas atoms were actually discovered experimentally because they change and because they're divisible, because they emit, there's a spectrum associated with them, and because they could identify the structure inside them, the nucleus with electrons going around. And the point is that the atom itself is not fundamental. It too has internal structure. And that internal structure is a nucleus with electrons going around it, and that nucleus itself is also not fundamental. There are more elementary objects called quarks, bound together through the strong nuclear force. So right now, really, as we speak, the experiments running are exploring a very tiny scale, the scale 10 to the minus 19th meters. It's the scale where the machine called the Large Hadron Collider is running. The Large Hadron Collider, the LHC, is a machine near Geneva at the French-Swiss border. It's 27 kilometers in circumference, and protons get accelerated around this ring. They go around 11,000 times a second. Every time they go around, they get accelerated a little more. And then the protons collide together at enormously high energy. And when they do that, they will be able to study both higher energies than have ever been studied before and smaller distances, this distance scale of 10 to the minus 19th meters. So it is the modern day microscope. It is the scale at which we're exploring today. And I'll give you somewhat of a flavor of what it is that we hope to discover there. But since we have this scale, let me just say that if we continue down, there are theoretical questions about even smaller distances smaller than any scale that we can hope to explore with any machine existing today or any technological tool. When you get to a small enough scale, 10 to the minus 35 meters, the world of quantum mechanics is taken over by a world of what's called quantum gravity, a theory that will combine together quantum mechanics and gravity, string theory being the best candidate. And I'll come back to talking about that for a few minutes later. But one thing I want you to notice about this tour, as opposed to the tour of the large scales, is that really we have different physical laws that become relevant at different scales. And one of the things that I find people get confused about is what that means. Are we really just replacing the old laws of physics, or are the old laws approximation of the new ones, which is actually the case? So I want to spend a little bit of time talking about how we organize this information, because it's a lot of information over a lot of scales. So like I said, what's most striking, at least to me about this, is that there's an enormous range of scales that we have there, 62 orders of magnitude. So we want to have a theoretical tool for organizing all this information. And there's a notion that we have called effective theories, where we keep track only of the effective quantities relevant for our observations and don't get caught in unmeasurable details. So rather than start by talking about physics, let's just look at a more intuitive example of what I mean. So I recently gave a talk at the 92nd Street Y, and if you wanted to find your way there from here, you probably wouldn't want to use a map that has the same detail as that map on the right. Google Maps makes this really explicit. You zoom in or you zoom out. And so you want to use the scale that's relevant for the question you have. If you tried to keep track of all of those small details, you'd never get here. You'd start off with a bigger map. By the time you got into New York City, you'd use the map on the left, but you'd start off here with maybe a map of the US. You'd find your way near to New York, then you'd get closer, and then you would use the details to find your way there. But you don't need that detail of the map on the right in order to find your way to New York. It's only when you have the resolution to actually experience the individual city blocks that you would care. When you're on a freeway, you don't care about all those individual city blocks. And I like using the New York example because I think New Yorkers sort of epitomize effective theories, because if you're in New York, your 3-block neighborhood is very different from any other 3-block neighborhood, whereas anyone outside of New York just says, we're going to New York City. So I think we all use this sort of effective theory of New York, while the New Yorkers are much more aware of the details. And it's a very general way of thinking. No matter what field you're in, you probably do divide up your thoughts into sort of big-scale questions and small-scale questions. If you're doing literature, you sort of have close reading versus following a story. You're doing psychology, you might look at nerve patterns, or you might actually ask about emotions. And what I want you to think about is the fact that even if we don't understand yet the relationship between those two, we know that underlying our emotions are our underlying physiological structure. So one of the challenges of science is to get from understanding the details of small scales to what's going on at larger scales. But sometimes science isn't as ambitious. We start off by just looking at the bigger scales, asking questions about them, and then ultimately we hope to derive it from the underlying structure. And the reason I emphasize this is because people will talk about nonsensical concepts like the theory of everything. And even if we could find all the underlying elements, that's not the same as answering all questions. You'd have to still understand how those ingredients feed into physics on larger scales. So although our science of elementary particle physics is looking down and trying to find out what's there, there are still these other questions of how it all fits together. That's just an aside. But in physics, of course, we use this idea all the time. When we learn how to throw a ball, I remember in high school, we were taught Newton's laws, and then afterwards we were told, well, Newton's laws aren't right, they're wrong. But they're not wrong. They work really well. In fact, if you're predicting the trajectory of a ball, you will still use Newton's laws. You don't need to use quantum mechanics. And in fact, if you did use quantum mechanics, you wouldn't predicted where that ball landed any more accurately from the point of view of any measurement you could possibly make. It's only if you had much greater precision, or if you were looking at that ball at an atomic scale, that it would actually matter. You'd have to either have the resolution or the precision to be able to see that difference. Otherwise, Newton's laws are perfectly okay. It's an effective description. It's an approximation. Ultimately, we know that this podium is made up of underlying matter that looks nothing like it. But that world of the atom isn't essential to when I'm describing how to move this table around, or this podium around. So if you think about it, that's kind of essential to how we're doing physics, because of course, we can't possibly know the answer to all the questions. We only know the answers about questions where we've had the resolution to study it. We can make theoretical conjectures about what's there, but that doesn't necessarily tell us what's there until we can make measurements. And if we couldn't ignore all those invisible ingredients, we wouldn't be able to proceed. So if you think about it, this is what I said earlier when we did our tour of small scales. If you take the atom that underlies this podium, you can then see what it's made of. It has a tiny nucleus surrounded by electrons. In some sense, atoms are mostly empty space, which means in some sense all material matter is mostly empty space. But of course, that's not what we see when we experience this hard tabletop. That's not how it appears to us. And that's why this physics seems so unintuitive. The laws operating at these different scales are very different than the laws that operate in our daily lives. And that's also what makes it so interesting to study. We're not just looking for the ingredients, we're really looking for what are the laws of physics that underlie what we have here. So of course, if we go inside the nucleus, we find that too is not fundamental. It has more elementary components, protons and neutrons, which in turn have further elementary components known as quarks. The up and down quarks are inside protons and neutrons, and there are heavier quarks also. And what we are trying to do is understand why are there all these ingredients, how they fit together, and how do the forces tie them together, and what are all these forces? Why do they have the properties they do, the masses they do, the charges they do? We're trying to put this all together. But I can't help but share a quote that I think really brings home how effective theories are. When I wrote my first book, Warp Passages, I realized that although I was writing a book for a popular audience, I hadn't actually read a whole lot of them. So I thought maybe I should just at least look around and see what they look like. And so people told me which ones they liked, and so I went and glanced around. And one of the ones was George Gamo's 1, 2, 3 Infinity, so I looked at that one. And there was this fantastic quote in it, which I think is both great and is showing the excitement and also is a cautionary tale. So the quote is, "Instead of a rather large number of indivisible atoms of classical physics, we are left with only 3 essentially different entities: protons, electrons, and neutrinos." And then he goes on, "Thus it seems we have actually hit the bottom in our search for the basic elements of which matter is formed." So it's very easy today to laugh at him and say, but I think it makes you appreciate just how your intuition gets sort of adjusted by the environment in which you live. He was living in a time when they had just discovered these nuclear elements. So they had discovered protons. They hadn't even discovered neutrons yet. But he knew about the nucleus and he knew about protons. And so he realized what a great breakthrough this was. They had developed these tools. They'd been able to discover these nuclear elements that were underneath what we see. Yet, he didn't have the vision to be able to realize that the time he lived also had its limitations. They hadn't yet been able to explore inside a proton or a neutron, which he didn't even know about. They couldn't look at these smaller scales yet. So it's really interesting to me that he could be so excited about having discovered fundamental structure, yet not think that this underlying structure exists. And it sounds really funny, except when you think about it in the time we live. It's very easy for us to also think, well, we know everything that's there. There's certainly no indication of any underlying structure yet. Yet, it would be really odd if we lived in the last time where we're going to make such a dramatic discovery. It's almost certain that there's physics that underlies what we see. And that's why research continues. And of course, in his case, he had completely missed the existence of quarks, which were discovered many years later, in fact. They were, in fact, motivated by theory to explain why there could be so many different elementary particles. The idea was there were these basic components that could be put together in many different ways. But they were eventually discovered by experiments, where they could discover this hard structure inside. And as I said, today, the frontier energy scale is 10 to the minus 19th meters, an even smaller distance scale. It turns out it's a really interesting distance scale because it's very likely to answer some very fundamental questions, which I'll tell you about in a minute. But here we see the ring. The ring is actually underground, so you can't actually see it when you're flying by, as some physicists mistakenly have said. It's underground. And what you see here is that there's the LHC, which is the Large Hadron Collider, but then at various points along this ring, the protons collide. So there are the protons going around, as I said, 11,000 times a second. It takes 20 minutes to accelerate them to their full energy. Then when they have that energy, they collide together. And when they collide together, they can form new matter. How do we know what's there? Well, at those collision points, there are experiments built around those collision points. And those experiments, the most important to me, are called ATLAS and CMS. They are general purpose experiments that try to just measure everything that comes out. Most of the time, what comes out is junk in the sense of ordinary, what we call standard model stuff that we know is there. What we're looking for is the 1 in a trillion event that goes beyond the standard model, that tells us there's something that goes beyond, that's new physics that underlies what we see. So one of the roles that I and my colleagues who are theorists have is to try to identify what are those distinguishing features that tell you there was something new. What is it? So they want to be able to both look for the standard stuff, but in order to identify what's new. So here's a small video that someone on the ATLAS experiment made. What you see are the protons get accelerated. They start in linear accelerated, then they go around a smaller ring, then a bigger ring. This is actually the tunnel, and this is the protons come down this beam here. You can actually go and visit, which I did before the machine was running, of course. Then the protons come, they collide, and when they collide, they're now inside a detector. and then whatever comes out goes through these various layers of detector to see what's there. And in fact, the machine is going to shut down in a year, and when the machine shuts down, will be a very interesting time to be able to go visit. You don't go visit when the machine is running, for obvious reasons, but you can visit the control room in some interesting places. But to actually walk through the tunnel, you can do before the machine was completed, and of course, once it shuts down, you'll be able to do that again. It's really fun to see what's going on there. So the Large Hadron Collider, as I tried to say, it's an exciting machine. It's the biggest machine ever, and it really is a machine that you need superlatives to describe, which I usually shy away from. So the first two quantities are things that make it distinct from a physics perspective. Why is this so interesting? Well, it's the highest energy machine. It's 7 times the energy of America's Tevatron, which was a Fermilab near Chicago that just shut down about a month ago. It also has what's called the highest luminosity. That's basically a measure of intensity. It's saying that you have a lot of collisions, so you can see rare events. So it has 50 to 100 times the luminosity. And when I say these parameters, it doesn't yet have them, and that's important to keep in mind when we hear news reports. The plan is for the Large Hadron Collider to run to the end of next year, shut down, and then come back up with increased energy and increased luminosity. So that's what we're waiting for. But to achieve these goals is really an amazing feat of technology. It has the coldest extended region that we know of. It's 1.9 degrees above absolute zero. To put that in perspective, it's colder than outer space. And the reason it's so cold is because they use superconducting technology to create the strongest magnets that are in industrial production. So there's 192 what are called dipole magnets that are placed around this ring. And the goal is to keep these charged protons at high energy inside the ring. And the higher energy they are, the higher magnetic field you need. So the challenge to building this machine is not so much accelerating the protons, because you can keep doing that every time they go around, but to keep them going around. And so the bigger the tunnel, the easier it is to do that, because you don't have to bend them as much. When the Large Hadron Collider was built, there was an existing tunnel. So their constraint was how strong a magnetic field they can have. And that's the constraint on the energy. So these magnets really are stretching technology to the limit. It also has the biggest, most effective vacuum that we know of over extended region. It's 1/10 of a trillionth of an atmosphere, less than on the moon. The pressure is less than on the moon. The reason you need that is because, for one thing, you don't want the protons scattering randomly, because you want them to be in collimated beams so that they're very focused and can hit each other. You don't want them to get all ruined as they go around. But the other reason is because if you had scattering, it would raise the temperature. And you don't want that to happen. That would quench the magnets. So they need a very effective vacuum. As I said, they're the strongest magnets in production. And the magnetic field energy is enormous. So it's just, when you see it, it's beautiful. It's a huge machine, but it has an amazing amount of detail in it, which is what makes it so impressive. As I said, the reasons for these extremes are for the physics reasons. You want to have energetic protons. We know E equals mc squared. So more energy means higher mass. It means we can see particles we've never been able to see before. It also means smaller distances, these distances of 10 to the minus 19th meters. We also want as many collisions as you can have. They're looking for rare processes, and your odds are better if you buy more lottery tickets. So basically, having more collisions means you're more likely to see something interesting. And as I said, you want to have machines detectors that are as precise as possible to measure everything that comes out. What will we learn there? Well, the big question that we might answer within the next year, if we're lucky, is how particles acquire their mass, how elementary particles acquire their mass. And that probably sounds like a very odd notion. I mean, why can't everything just have mass from the get-go? It turns out, if that was the case, you would end up making nonsensical predictions. Probabilities of interactions greater than 1, things that just don't make sense. So we know there has to be a mechanism that explains how elementary particles get their mass, and that mechanism is called the Higgs mechanism. It's named after the physicist Peter Higgs. And the experimental consequence of this would be something like a Higgs boson that you might have heard about, the search for the Higgs boson. It's a particle associated with this mechanism. It's not the only possible way this can happen. Essentially, what the Higgs mechanism does is it essentially spreads a kind of charge throughout space, and particles acquire mass by bouncing off that charge. It's not electric charge, it's some sort of mysterious charge that's part of what's called a Higgs field. The question is, what is it that distributed that charge throughout the vacuum, throughout empty space? And that is what we're looking for when we look for the Higgs particle. We're looking for that sector of the theory, that portion of the theory that is responsible for this. And the Higgs boson is one possible experimental consequence that we might learn about very soon. We'll almost certainly learn about within the next year, something. We'll either learn that this elementary theory is wrong, or we'll learn that it's right. It's very exciting. Another question, which seems far removed but is actually somewhat related, is why is gravity such a weak force? Now, gravity might not seem weak when you're climbing up a mountain, but if you think about it, you can jump up and down, even though you have the entire Earth trying to pull you down. And the fact that you can pick up a paperclip with a tiny magnet shows us that the force of electromagnetism is far greater than the force of gravity. And that's, from the point of view of elementary particles, gravity is totally negligible. It's completely weak compared to the force of electromagnetism, 40 orders of magnitude smaller. So the question is, why is that? Can we understand this weakness of gravity? In the process of trying to answer that question, we can learn something very deep and fundamental about not just particles, but the nature of space itself. Is there more symmetry out there in the universe than we thought? We know about symmetries that, for example, say it doesn't matter in which direction I orient my experiment. That's called rotational symmetry. But that symmetry might even be extended into the quantum regime in what's called supersymmetry, which is one of the targets of searches. Another idea familiar to anyone who read my previous book too would be an extra dimension of space. There could be an extra dimension of space that could help explain this weakness of gravity. And the final thing that we expect perhaps to learn, that we have reason to think we might learn something about, is the nature of dark matter. The matter that, it's matter, it clumps, it's out there. There's 6 times the energy in dark matter than the matter that we're made up of. But it's different because it doesn't interact with light. It interacts gravitationally, so we know it's there, but we don't know at a fundamental level what it is. So that's one of the questions we're trying to answer. Now, because I talked about effective theory and because I'm asked this a lot, I'm going to mention string theory. String theory is not going to be studied at the Large Hadron Collider. String theory applies at scales far removed. We talked about 10 to the minus 19th meters. String theory has visible effects, most likely, at 10 to the minus 35 meters. That's 16 orders of magnitude smaller scale than what we're studying at the collider. So we really have to put on our effective theory hats, because I'm telling you that even though underlying all of matter could be elementary particles, or it could be elementary strings, things that seem in principle very different. If those strings are only 10 to the minus 35 meters long, you can't tell the difference. They look like particles from the point of view of something with resolution of 10 to the minus 19th meters. Furthermore, the difference between a string and a particle is that a string can oscillate in different ways. That means there could be a whole bunch of new particles. But those particles are 16 orders of magnitude too heavy to produce. So the reason we talk about string theory is not because of experiments, but because there's a theoretical puzzle, a puzzle of how to combine together quantum mechanics and gravity, not at the scales we see, but at the scales 10 to minus 35 meters. It's a scale that's very far removed. Ordinarily, I can say when I do particle physics, I could ignore gravity. When I do cosmology, I can use gravity and ignore quantum mechanics to some extent. But it's at these scales, that are these really tiny distance scales, that we would need to have both. So there are theoretical reasons to study string theory, but not yet experimental reasons. So we really have to have our effective theory idea, this idea of scale, that tells us this is much too small a scale to be visible, yet could underlie what we see. And because I'm talking about scale, I'm going to tell you one thing which is completely unrelated, and you're really going to have to put on your effective theory hats. Because it actually, you might ask, I told you why that we had this biggest scale of 10 to the 27th meters for the visible universe. But I also had a smallest distance scale, 10 to the minus 35 meters. Why did I say there was a smallest scale? Well, this, again, is theoretical speculation. I don't know that this is true. But, excuse me, I do have allergies, that I know is true. But there are reasons to think that the notion of distance itself, of length itself, might break down at the scale of 10 to the minus 35 meters. Why do we think that? Well, we don't even know in principle how we could study a distance of that scale. Now, why do I say that? Remember at the beginning of the talk, I said that we need a small wavelength to study short distances. Well, to study a distance as small as 10 to the minus 35 meters, you would need a very tiny wavelength of that size. But to get a tiny wavelength, you need a high energy wave. That's why we have high energy colliders to study short distances. If you think about it, a high energy wave has a higher frequency and a shorter wavelength. So if you had enough energy to study 10 to the minus 35 meters, you would have so much energy inside a small distance that you would make a black hole. Now, we don't care about the black holes. What we do care about, for this argument, what we do care about is the fact that if I then added more energy, instead of studying a shorter distance, I would get a bigger black hole. So we don't even know in principle, how to make a probe to study a distance of that size. And there are other arguments, too, that make us think that the notion of distance itself might break down at this scale. And again, you might say, well, that sounds horrible. How can we have distance breaking down? But again, we don't operate at those distance scales. We are safely away from those scales. We're at much larger scales where things appear to be continuous length, continuous distances. So again, we have our effective theory notions, but it's just an interesting fact if we're thinking about grading things according to scale. But I'm not going to say any more about that. This is what I said earlier. I'm going to skip that slide, but we can come back to it. I'm just going to say the goals today. The goals today are, in general, always in science, to go beyond the established theories and find the missing pieces. In this particular case, it's a really exciting time because we really do have experiments. The LHC is something that's been in development for over a quarter of a century. We also have very interesting experiments studying dark matter and dark energy going on today. So we really are poised to learn more, not just with theory, which we've been doing for years now, but with experiments. So we want to make discoveries that can't be explained within the current framework, in our case, the standard model of particle physics. And we want to use experiments to choose among the potential underlying theories. We're not just looking for experiments to verify ideas. Some of them will rule out ideas. And in my book, I talk a lot about what are the guides we have where we're trying to go beyond the standard model, both in theory and with experiment. And we're going to probe new energy and distance frontiers. So I'll just show you one more video here, which is just the continuation of what we had before. Those protons collide, the particles come out, and they go through different layers of the detector, measuring different things: charge, momentum, energy. And based on what each of those layers measures, they try to identify which was the particle. In this case, the video was made to show a particle of the standard model known as a Z boson. It's a particle like a photon, but in this case it's heavy, and it decays to an electron and a positron. So the way you find that particle, which is the way you find a lot of new particles, is you look for the decay products. You look for what came out. In this case, an electron and its antiparticle, a positron, and you put it together to find out what was there. And that's what they'll be doing when they're looking for new particles as well. And this is just proof that I was there. So before I close, I just want to tie these ideas back with what I talked about in the beginning, namely my name on a poster. So I'm just going to say one more big physics idea. And again, I'm going to go through this rather quickly, but I just want to give you a flavor for the kind of exciting new ideas we'll be looking for. I'm going to say this very quickly, but one of the things we could actually search for experimentally is a new dimension of space, a dimension of space beyond the three we're familiar with, beyond left, right, forward, backward, up, down. a genuinely new dimension of space. Why would we even consider such a thing? Well, one is we actually don't know that there are 3 dimensions. The history of physics has taught us anything. It's that unless you look, you're not going to find things. But when you do look, you have surprises. And in fact, Einstein's theory of gravity works for any number of dimensions, not just 3. So there's a real possibility that there could be dimensions beyond what we see. Another reason is string theory. String theory claims to unify quantum mechanics and gravity, but it doesn't work if there are only 3 dimensions of space. If string theory is right, you need dimensions beyond the 3 that we know about. But perhaps the best reason to think about it is we have a chance of understanding connections among physical parameters in our universe. And in particular, this question about the weakness of gravity is a question that's been around for decades. And we've tried to solve it, and not just we, means the entire body of theoretical physicists have looked for solutions. And there's no completely satisfactory solution. So at that point, it makes sense to look beyond and see, are there some exotic ideas that give a nice explanation? And the one additional ingredient that comes into this is something called a brain world. The notion is based on the word membrane. So it's a lower dimensional world inside a higher dimensional one. In this case, it could be that we live in 3 dimensions inside a higher dimensional world. And the reason my collaborator Raman Sundram and I were excited about this idea is we realized that if you had not just one brain world, but 2, an extra dimension, it could naturally explain why gravity is so weak. It's obviously not something that I can go through right now, but we just solved the equations of general relativity in this context. And I should say that these brain worlds come naturally out of string theory, but they're not necessarily proof of string theory. But these brain worlds do come out of that context. And we found that gravity varies exponentially in a different dimension. So even though gravity could be really strong, very nearby, and by very nearby, I mean a fraction of a centimeter, 10 to the minus 30th meters away, really close, we wouldn't know about it yet because it interacts only gravitationally, and gravity is so weak. Yet it could explain why gravity is so weak in our universe, because it's exponentially falling as it goes across another dimension. And to return to the theme of scale, what's really going on is that your measuring stick is changing as you go across an extra dimension. So something that you expected to be very heavy, in fact, could turn out to be extremely light, and therefore gravity is so weak. Now, this is a theoretical idea, but what's amazing is that even though it sounds so exotic, it has to do with an extra dimension and warped extra dimensional space, it actually has consequences for the Large Hadron Collider, as do any potential explanations of the weakness of gravity. In this case, it's something called the production of something called a Kaluza-Klein particle, a particle that travels in the extra dimension, has momentum and energy associated with the extra dimension. It appears to us like a heavy particle that, just like that Z boson, would decay inside the detector into, in this case, an electron and positron, but into many other particles. And by looking at the different ways it decays, one can determine, is it this particle associated with an extra dimension? So we have a real chance of answering this, probably not before the machine turns down, shuts down, and comes back on. But once it comes on at full energy, they can do a real search for these particles. So I just want to say a quote. Of course, Steve Jobs was in the news a lot. And so again, I'm sort of misappropriating it. He was talking about his life at the Stanford commencement speech. And he said, again, you can't connect the dots looking forward. You can only connect them looking backwards. So you have to trust that the dots will somehow connect in your future. And again, I think it's a nice statement about science, because we sort of have a hope that we'll see something, we have ideas, but we don't know until we've actually done the experiment. And of course, in the case of particle physics, it's literally connecting the dots to see what those tracks were and find out what was there. So we're waiting to see. Maybe these ideas will be shown to be real. It's going to be an interesting few years where we get and interpret results. Some of these ideas are really elegant and beautiful, but that's not good enough, and we want to see. So I'm just going to spend the last few minutes just tying together with what I had in the beginning. So I'm going to talk about how these ideas were realized in a couple of projects I did. not physics, but in art projects. And it's not teaching the physics, as some people seem to think it is, but really just introducing the concepts. So there's an art show actually going on at the Carpenter Center right now that moved from LA. It's called Measure for Measure. I curated it with Leah Halloran, an artist. And it was really designed to illustrate the theme of scale. So Barbara Pomade did this enormous sequoia tree. But what she did is she did it as a sequence of small pictures. So if you focus on just like the Eiffel Tower pictures in the beginning, if your focus was on the left, it's nothing like what you see when you go to the picture on the right. And each of the pieces, this was a very literal way of doing it, but each of the pieces illustrated this theme in their own way, whether it's economic scales from someone who gave out cupcakes to sort of art, someone who had faces in sort of a pop art looking thing. So you can actually see this at the Carpenter Center. It's up for the next month. It just opened up. But to get back to the affiche, that was because Hector Parra, who's a composer, asked me to write a libretto for a small opera. So I will just amuse you by letting you see some of what was in that opera. So I'll play some of this and I'll talk about some of the themes, which were basically how people see the universe, what it means to do experiments, to really explore what creativity meant, what discovery means, and what drives it. So it was both sort of used literally in physics to sort of guide Hector's composing and Matthew Ritchie's sets, but it was also just an abstract way to sort of metaphorically talk about an extra dimension as a way of exploring. So I'll just show you a little bit of that, if I can. Has an actual equation, he insisted on it. So basically it was the comparison between the way the two of them see the world and what drives you to discovery and what drives you. So she got to explore this more colorful, wider, extra-dimensional world while he lived in a smaller world and tried to understand it. But it's also interesting from the point of view of understanding what an experiment means. Because in a sense, we're not going to the extra dimension. It's coming to us, and we're trying to interpret what's going on and what's there. So in my book, I'm not just talking about the physics that I present today, but I'm talking about what goes into scientific thinking. What are the roles of creativity and discovery? What is the role of scale? But also, what is the role of uncertainty when we're doing science? And it's really important because I think science often gets abused in the popular press, and it's not understood that uncertainty is part of presenting a scientific result. And also, I talk about how we actually do our physics. I have a chapter called Truth and Beauty and Other Scientific Misconceptions. What is actually the role of beauty when we're doing science? But of course, it's also what we're exploring today and what is the physics we hope to explore. So we've come a long way, but there's a lot to learn. So I just close with one final picture that I saw when I was in the Tate Museum, which I think really nicely illustrates the idea that we can be living in a world where there's riches yet to be explored. What I didn't know when I saw this picture was that's actually the Chateau de Sion, which is very close to CERN, that houses the Large Hadron Collider. So clearly, it's not a coincidence. So I will thank you.